Good evening, everyone, and welcome back to session number 2 of the Math of the Cell. We have here with us Ondrej Maxian. And so, Ondrej, if you're ready, we'll go ahead and get started.
Okay, hi everyone. Welcome back. Thanks for coming back. We got about a 50% return rate, which is not great, but it is what it is. So nice to see those of you who are here. So before I start, does anybody want to ask me anything about last session? Okay, no questions? All right, so yeah, last time we talked about basic numerical methods for solving equations. So last time we talked about basic numerical methods for equations. This time I'm going to talk about what equations are we actually going to solve. And so those are the equations of fluid mechanics. So I wanted to give a basic overview of fluid dynamics. Okay. So what do people know about fluid? Do people know anything about fluid dynamics here? Okay, Carolina says nothing. Nicoletta, do you know anything about fluid dynamics?
Not really. I don't think so.
But you both have had ODEs, right?
Yeah, I'm taking it right now.
I haven't taken it. I'm in linear right now.
Oh, you're still in linear algebra. Okay. Bao, have you had ODEs?
Yeah, I'm taking PDE right now, but
Okay, good. So you'll understand more of this than the other two, because there are PDEs involved. So, well, you've had Calc 3, right, Carolina? Okay. All right. So what I'm going to talk about is I'm going to talk about some fluid. Okay. Here's like a blob of fluid, and I'm going to call a position in the fluid X. And it has coordinates x1, x2, x3. So we're in 3D. And I'm going to call the velocity u, and that also has three components, u1, u2, and u3. So the fluid velocity u is a function of the position in the fluid x and time. So there are two different ways to think about the way a fluid moves. The first way is what we call the Eulerian frame. So in the Eulerian frame, what you have is think about that you're in a room and you're trying to measure the temperature of the air. So what you have is you would put sensors on the walls. Okay, good. So Nicoletta learned this. So in the Eulerian frame, you put sensors on the walls and you keep the sensors fixed. So you have fixed sensors and you're looking at the way the fluid is moving by them. The second way is the Lagrangian frame. So Nicoletta, you say you learned this, right? Do you know what the Lagrangian frame is?
I think that's when the sensors aren't fixed, so it's like going sort of with the velocity.
That's right. So that would be like if I tied the sensors to balloons. and I had them just flying around the room. So they're moving with the velocity of the balloons, and they're tracking the temperature as they move. So the question is, how are these two related? Well, first we want to talk about how does a sensor move in the Lagrangian frame. So we're going to assume that the flow U is known. And I'm going to call x of t the position of the sensor as it moves with time. And I'm going to call x of 0 equal x naught the starting point. So that's where the sensor starts out at time 0. So the idea is that the velocity of the fluid is known here. So somebody tell me, what is the change in the position of the sensor with time? How do we say that the sensor moves? Yes, value yes. The sensor moves with the local fluid velocity. So it moves wherever it is, it's moving with that local velocity. And the position at time 0 is x0. So this here, this is an ODE for the position of the sensor with time. Now, there are some codes, right? There are some fluid dynamics codes that are so-called Lagrangian codes or particle-based codes. So what happens is they analyze the motion of a fluid by just taking a bunch of particles, dumping them in, and seeing how they move. So that's one way to do it. That is not how most good or most of the famous or high-level computational fluid dynamics codes work. Most of them take on an Eulerian perspective that I'm going to talk about next. So the next thing that we want to talk about is the relationship between the frames. So let's call F some quantity that we're interested in tracking. So like for the balloon example, it's the temperature. And what I have is, so f of little x comma t is the Eulerian variable. That tells you if you have fixed sensors here is the quantity, though the temperature, at each sensor as a function of time. But then I have the Lagrangian variable, which is when I put my sensor in the balloon, I have the temperature at the sensor locations, which change with time, and then also as a function of time. So now here's a calculation that I think you can do. So what is the derivative of f if I consider this quantity here? F is a function of big X of t and t. What is the derivative of f with respect to time? Suppose you had a function like, let's just do a quick example, right? Let's say that f was x of t squared plus t cubed. What would be, in this case, df dt? Good, okay. So Bowie said, Bowie, feel free to unmute yourself. It's better for me than just talking to nobody. So feel free to mute yourself and call out. So the first thing you do is you apply the chain rule on x of t, and then you have the x prime of t. So you differentiate x squared, and then you have to do x prime of t. And then you add this derivative of t cubed. So if we think about f as a function of x and t, and in 3D, we're going to have f as a function of x1, x2, x3 of t, where these guys, these x1, x2s, x3s, those are all functions of time. What you wind up with is that the derivative of f with respect to time is partial f, partial t. That's this term here. Plus partial f, partial x1, partial dx1 dt, plus partial f, partial x2, dx2 dt, plus partial f, partial x3, dx3 dt. So all this is just the chain rule. And I should be using here, I should be using capital letters because this is the Lagrangian variable, big X. So this can be written in terms of vectors. This can be written as partial f, partial t, plus, what do we call this vector? What do we call this vector right here? Calc 3, come on. Carolina, you had Calc 3. You remember what this is called? Give me a good guess. Starts with a G.
So it should be gradient.
Yes. It's the gradient of f. So this is the gradient of f. And then this here, dx dt, this is just dx dt, the derivative of the flow map with respect to time. But that is the fluid velocity u. So the conclusion is this here is the fluid velocity u. So the conclusion is that the derivative of the Lagrangian f, so this is the derivative moving with the sensor, is equal to the Eulerian derivative with respect to time at a fixed location plus the gradient of f, I'm going to call it, plus the fluid velocity u dotted with the gradient of f. So this is this is an operator. So if I have this df dt plus u dot grad, so this is ddt plus u dot grad of f. And this guy here has a special name, this operator. Have any of you heard what it is? It's called the material derivative, and it's usually denoted with a capital D. So this is ddt of f. So this is the material or substantial derivative of f. So what this is how f changes when you're moving with a sensor. So I'm moving with the sensor, but I'm stuck right here, and I want to know, how does my derivative, the derivative that I measure, relate to the Eulerian quantities around me? Well, the derivative that I measure is the change in f at this specific point with respect to time. That's this term, plus the change in f with space as I move with the velocity field. And that's what this term is. Make sense? Okay. So I don't know about you guys, but I think that this, so far, Calc 3 is all you need to kind of understand this, right? Just multivariable calculus. So the next thing we're going to talk about is conservation laws. So when you're in a fluid, right, in the real world, what are some things that are conserved? Let's think about like in life. What are some things that are conserved? Energy, good. So energy is a conserved quantity. Energy cannot be created or destroyed. Momentum, yes. Momentum is a big one. There's another thing. There's only one person, he lives way upstairs, who can create mass out of thin air. That's right. Not even Harry Potter could create food out of thin air. Right? But Jesus could, supposedly, we think. So, anyway, these are the things that are conserved in life. And the momentum and the mass, the conservation of mass and momentum, are the two equations that fundamentally govern fluid mechanics. So if you think about energy, you can write an energy conservation law for the fluid. But I'm pretty sure that energy is mass times momentum, right? Or mass times momentum squared or something like that. So momentum is m times v. So energy is momentum squared over mass or something like that, 2 times mass. So you can relate the energy to the momentum. So what we want to derive is we want to derive equations that describe the conservation of mass and momentum inside of a fluid. And once we do that, then next time we can talk about how do we solve those equations? How do we figure out how the fluid is moving? So, any questions on that? Let's start with mass. So, let's say that I have a control volume. They call it a control volume. Okay, I'm just going to take an arbitrary volume of the fluid, a box that looks like this. All right. And I'm going to call, so first of all, the rate of change, I'm going to call this box omega, okay? And the boundary of this box I'm going to call that gamma. So omega is the interior of the box, and gamma is the boundary of the box. So I'll try to draw this arrow inside, but not very good. Yeah, that looks all right. Now, what's the rate of change of mass inside the box? And I'll give you a hint. You can write it in terms of density. First of all, what is the mass inside the box in terms of density? Let's start with that. What is density? Mass divided by the volume. Yes, Joe. Density is mass over volume. So if we want to calculate mass, it's just rho times the volume. But what we're going to do is we're going to assume that we don't really need to know the volume of the box. And we're also going to assume that the density could vary inside the box. So what we actually have to do is we have to integrate over the volume of the box, the density, and I'm going to write dV because it's a volume integral. And ddt, if I just take the time rate of change of that, that's the rate of change of mass in the box. Okay. Now, it's possible somehow, it's not going to be possible for mass, but for other quantities, that you could have a generation of mass in the box or consumption of mass. So I'm going to call S the rate of consumption of mass per volume. Now, so far we have the rate of change of mass into the box. Then we have the amount of mass being consumed or generated within the box. But how else could the mass within the box change? What could happen to it? There's a fluid here. So what could be happening? Think about if you had don't think about it as mass, think about if you had like a sugar or something inside the box, this box, and I turn the box over and open the lid or something. What happens to the sugar? Okay, no problem, Carolina, bye. And then there were 2, 3. Okay, so what else could happen in the box? Relating to density? Not necessarily. I'm just talking about things. So far we're figuring out how does something change the amount of something inside this box. So let's say we had like sugar in the box. How could the amount of sugar change? Sugar dissolved in water, right? So we talked about it could be consumed in the box, like in a chemical reaction or something, or it could be generated in the box in a reaction. But there's a sort of considering that there's more fluid over here, right? There's another obvious way that not obvious, but there's another way that sugar could change, the amount of sugar in the box could change. More could enter, yes. It could enter or leave with the fluid velocity field. So what could happen is that fluid could carry mass or sugar, etc., out or into the box. So if n is the outward pointing normal vector, the speed of the fluid on the box boundary is u dotted with the normal vector. The speed of fluid leaving the box. Right? Because if u is just traveling along the edges of the box, if the velocity of the fluid is just along the edges, no fluid leaves the box. You care about the component of the velocity normal to the box. And what happens is this u dot n, it advects with it the sugar, for example. So the rate at which mass leaves the box per area is U dot N. So this is the rate of water leaving, the rate that the fluid leaves, multiplied by the density. And you can think of that sort of as a concentration. So it's the concentration, in this case, of mass per fluid volume. So that is the rate at which mass is leaving the box. And in order to, this is per area. So this is the rate in a little tiny patch of the box with size dA. So now in order to get the full amount of fluid that enters or leaves the box, the flux, yes, this is a scalar quantity, Chella. So this whole thing, this is a scalar. That's right. It's the flux of mass leaving the box. Thanks for the question. Flux per area, and then I integrate over the area to get the total amount of mass that leaves the box. Mass is conserved. What does that mean? It means that the rate of change of mass in the box is equal to what? The mass doesn't change, good. Okay. The rate of change, well, not necessarily zero, because mass could enter or leave this box. But we know that the rate, not necessarily constant, the rate at which the mass leaves the box has to be equal to the amount that enters minus the amount that leaves, plus the amount generated minus the amount consumed. That's it. That's all that happened. So I think starting with mass might not have been a bad idea. If I had to start again, I would start with something like sugar. So the rate of change of, say, sugar inside of this small, tiny volume of fluid is equal to the amount of sugar entering minus the amount leaving plus the amount that reacts or is generated by a reaction inside the box. And we already introduced letters for this. So the rate of change, I'll highlight in red, that's this term. And that's going to be on the left side of the equation. The rate of consumption is this term. And that's, we can also treat that as net consumption. So we can say that that is equal to the amount consumed minus the amount generated. And then the rate leaving or entering the box, oops. The rate leaving or entering the box is this light green term here, the flux, in or out. So we can write our equation here, ddt of the integral in the box of rho dv equals, this is the rate leaving the box. This is the rate of change inside the box. So positive is more mass. So if it leaves, it's negative. So we need a negative sign here over the area of the box, u dot n times rho. So I'll write that as, I'm going to write that as rho u dot n. And then I'm going to subtract inside the box the rate at which there's consumption. That's S, the rate of consumption. Now, does anybody remember there's a special theorem from Calc 3. If you have an integral over the area, so this is dA, this is dV. If you have an integral over the area of rho u dot n, so the key here is dotted with the normal vector, that is equal to some volume integral. And does anybody remember what that is and what theorem that's called? It's a very important theorem. We use it all the time in applied math in general. Starts with a D.
It's the divergence theorem.
Yes, thank you, Chilla. The divergence theorem. And do you remember what it says? It says that the integral of rho u dot n with respect to area is the same as the volume integral of the divergence of rho times u dv. So this is the divergence. And what it means is that u is a vector. So when I take the divergence, it means I'm taking the derivative of u1 with respect to x1 plus the derivative of u2 with respect to x2 plus the derivative of u3 with respect to x3. So now I'm going to change this integral here into a volume integral. So now I have d dt of the integral of rho dv equals the integral with respect to the volume, negative, delta dot rho u minus the integral with respect to the volume of s dv. And now all of my integrals are over the same control volume, and the control volume doesn't change in time. And because it doesn't change in time, I can move this time derivative inside the integral. But the density is a function of space and time, so I have to replace that with a partial derivative. And then I can move these integrals to the other side and just write one integral. And now the control volume, so this volume that I took here was arbitrary. It could be any box anywhere. I could make the box any size. I could shrink it all the way down, make it bigger. Because it's arbitrary, it means that if the integral over an arbitrary domain, a domain of any shape and size, is 0, it means that the function inside has to be identically 0. So that means that this function d rho dt plus grad dot rho u plus s equals 0. So this equation is conservation of mass. In a fluid. And specifically in a fluid, there's no generation or consumption of mass. You can't just generate mass. You could generate sugar in a reaction, for example, but for mass, you cannot. So typically we drop this plus s term, and this d rho dt plus delta dot rho u equals 0 is called the continuity equation. It's the first equation that describes fluids, the flow of fluids. Now, let's suppose that the fluid has a constant density. I have to plug in my iPad. Right, most fluids have a constant density. So that is the density as a function of x and t is just fixed to a constant. What does this equation simplify to? Yes, so d rho dt is 0. So now you have delta dot rho times u is 0. But rho is a constant, so I can pull that out of the divergence. So now I have rho naught delta dot u is 0. But now rho is a non-zero constant, so I can just cancel that out. So what I get is delta dot u equals 0. So this is called the equation of an incompressible fluid. Incompressible meaning the density is constant. It can't be compressed. It always has the same density. Now there's the definition of incompressible is actually slightly different than this, but I'm just trying to simplify it. So for an incompressible fluid, you get this equation. The divergence of u is 0. So this is your mass balance for cells, for example. For the fluid within cells, that's the mass balance equation. And there's another equation which is called the momentum balance equation. And I'm going to just write it down. I'm not going to derive it because we're low on time, number one, and the derivation is kind of complicated. So the momentum balance equation is rho times partial u partial t plus u dot gradient of u. Now gradient of u is a matrix because u is a vector. So this is a vector dotted with a matrix. So this is a 1D dotted with a 2D. So the result is 1D. And that equals something called the viscosity of a fluid times del squared of u minus the gradient of something called the pressure plus any external forces that you have, things like gravity. And here, this Laplacian, what it means is it means the derivative of, it's a vector and it has components that look like this. So for each component, it's just the Laplacian of each component. And then together with this, you have delta dot u equals 0. Does anybody know what these equations are called?
Navier Stokes equations.
That's right. Thanks for joining us, Mengjian. They are the Navier Stokes equations. Have any of you seen the movie called Gifted? It came out a couple of years ago, 2017.
I think I saw half of it, but not the whole thing.
Yeah, good movie. Good movie. It was about this family where the grandmother was this famous mathematician, but she married somebody and moved to America with him, and her math was all lost. And so she raised her daughter to solve the Navier. Her goal was for her daughter to prove that the solutions to Navier Stokes exist and are continuous or blah, blah, blah. And her daughter committed suicide, and she had another daughter, her granddaughter, who was 7, who the grandmother was trying to raise to do the same thing. But the grandmother's other son, not the daughter, committed suicide, so her brother was raising the little girl, and he just wanted the grandmother to chill out and let her be normal. So that's the kind of premise of the movie. I recommend it. It's a very good movie. I enjoyed it a lot. I just watched it a couple weeks ago. But they talk about Navier Stokes. So this is a problem of tremendous theoretical study. A lot of people way smarter than me are studying it because they're trying to figure out if solutions to this equation actually exist. Like if you can prove that they exist. We're going to figure them out numerically, but can you prove that they exist? And that's like a tougher question. So there's a guy named Vlad Vikol. Do any of you know who that is? He's a professor in the math.
Yeah, he's doing convex integration on this, right?
He what?
He's doing convex integration on this.
That's right. So he is trying to prove, he is working on that problem. Apparently he's doing pretty well from what I heard, but maybe he'll figure it out. He's like a genius. So that's that. That's about Navier Stokes. Anybody want to ask? Because I know that in the popular culture, you hear about Navier Stokes all the time. So the thing about Navier Stokes, though, is that at least in cells, some of the terms are not really significant. And let me see if I can give you an idea why. What I want to do is I want to make an estimate. I want to estimate the importance of each of these terms. And to do that, I'm going to do what's called a scaling argument. So how many of you, I know those of you who are taking ODE with Professor Hamoud right now, because I'm the TA, have done this, but how many of you have done scaling or non-dimensionalization before?
I have done that.
Okay. So only one of you?
I did it with Professor Hamoud last semester.
Okay, good. 2 of you. So half of you have done it. So here's the idea. We're going to estimate each quantity in this equation. All right? And how we're going to do it is we're going to say that the velocity is equal to some velocity capital U, which is somewhere between 0 and 1, or on the order of 1, times some characteristic velocity, which I'm going to call U bar, okay? Now that is the number that has dimensions. So for cells, I'll give you an example. It's like 10 to the negative 6 meters per second. That's the typical velocity of a cell, of things inside the cell. Same thing, the density, typical density is water. It's 1 kilogram per meter cubed. Typical viscosity is 1 kilogram per meter times second squared, also known as 1 Pascal second. I think this is, I think the second squared is in the numerator. No, it's not, it's in the denominator. That's right. Yeah. And then the length, I'm going to estimate length, or x, dimensions of x. I'm going to say that x equals L times x bar. And x bar oh no, sorry, I got this all messed up. I'm going to say that little x equals big X times L, where L is the characteristic length. Again, for cells, that's like 10 to the minus 6 meters. So what we're going to do now is we're going to rewrite the equation in terms of these dimensionless quantities. And I'll estimate time by capital T times, the time scale is the characteristic length divided by the characteristic velocity. Okay. So now I'm just going to plug in those estimates into the equation. And what I get, like for example, I have a term like du dt. If I plug in for u, that becomes d capital U dt times u bar over L over u bar. So that's u bar squared over L. So the reason times capital U dt. So the reason I'm doing this is because I know that this term, based on my scaling argument, I know that this term is somewhere like around 1. This is like around 1. And this term tells me exactly how big the dimensional term is. Okay. So if I carry this out for this equation, for the Navier Stokes equation, what I get is rho big U, U bar L over mu. Oh, sorry. Rho, so here you have a du dt, and I'm going to multiply that by rho. So I get rho U bar squared over L times du dt, d capital U dt, d capital T, plus the gradient of capital U dotted with the capital U equals mu times U bar over L squared times the Laplacian of capital U minus the gradient of the pressure plus the external force. Now what I'm going to do is I move these terms over to the other side. So I get rho U bar L over mu times this term here equals delta squared U minus this 1 over this stuff. So I'll just write it as something P bar, P tilde plus F tilde. Now, the reason I don't care about the scaling of the pressure and the force is because I don't know how big they are. I have to keep them in the equation because I have no idea how big my force is going to be, and I have no idea how big the pressure is going to be. So I'm not going to mess with those. But what I am going to mess with is the relationship between this term and this term here. Now, this term out front, the density times the typical velocity times the typical length over the viscosity, has a special name in fluid mechanics. It's the most famous number in fluid mechanics, I would say. Does anybody know what it's called?
Reynolds number.
That's right. So this is called the Reynolds number. So let's estimate it for a cell. It's just called RE. So for a cell, I told you that the typical density is 1 kilogram per meter cubed. The typical velocity is 10 to the minus 6 meters per second. And the typical length is 10 to the minus 6 meters. Were you going to say something? Okay, sorry. And the typical viscosity, as I realized that I just messed up the unit, this should say kilogram meters per second. The typical viscosity is 1 kilogram times meter, or kilogram over meter times second. So this number comes out to be dimensionless, and for cells, what is it?
It's 10 to the negative 12.
10 to the negative 12. Really, really small. So what that means in practice is that this whole term over here on this side of the equation can be neglected for cells. It means that I can replace this first equation of the Navier Stokes equation by just the right-hand side. So it's mu Laplacian of u minus grad p plus f equals 0. That's it for the momentum balance. And this equation also has a name. Does anybody know, do you know that one, Mengjian?
Stokes equation.
That's right, this is Stokes equation. Did you have fluid mechanics already?
Yeah.
Okay, so that's why. So this is called the Stokes equation. The Stokes equation, I just want to make one comment about the Stokes equation. The time dependence is gone. There is no time dependence in the Stokes equation. What it means is that at every instant in time, you're on a length scale that's so small that at every instant in time, the flow immediately responds to what you're doing. So think about swimming freestyle, right? I like to swim. So when I swim freestyle, the reason why it works so well is because I start the fluid going backwards and it continues to go backwards as I pull. So even as I recover my arm outside of the water, I'm not grabbing the fluid at all, but it's still moving backwards because I pulled it and then I recover, but the fluid keeps going this way. Well, in Stokes flow, that's not how it works. In Stokes flow, I pull like this, and then once I lift my arm out of the water, once I stop pulling the fluid this way, the fluid just stops. It doesn't know about what happened to it a second ago. So it's a lot harder to swim in Stokes flow than it is to swim in Navier Stokes, in regular old Stokes. Okay, so I'm done. That's it for today. I'm sorry it might have been a little dry, but I wanted to make sure we got some basic understanding of the equations that we have to solve. And then next time we're going to talk about how do we solve these equations, I'm going to say on a periodic domain. So we have this equation, and then we have the mass balance equation that we have to solve together. It's a system of equations in 3D that we have to solve for the velocity, that's the first unknown, and the pressure is the second unknown.
Thank you so much, Ondrej. A really interesting session. And thanks everyone for attending. Our next session with Ondrej is going to be on Wednesday, March 17th at the same time, 6 p.m. Eastern. So hope to see all of you guys then, and thanks for coming.
Any questions from anybody before we go? Okay, so thank you. See you in 2 weeks then.